general relativity, step by step. I've written down the Einstein field equations under the assumption of linearity, so we're considering small perturbations h alpha beta to the metric tensor in flat space, or the standard metric tensor in flat space, equals my real metric tensor g alpha beta. And I'm assuming that that is small, and I'm using the fact that this is constant over and over again. So you'd expect that the equations would be a lot simpler, and they are a lot simpler, but they're still incredibly bad. They are much, much, much simpler than the full nonlinear Einstein field equations. They're linear though, which is a good start. So how are we going to solve them? Well, they're quite bad. What we need to do is and I wouldn't have spotted this at all, I'm not quite sure where the idea came from. What we need to do is to define a trace reversed h. And I'll show you how that works now. What I'm going to do is define h bar mu nu to be equal to h mu nu minus a half eta mu nu times h, where h equals g alpha beta h alpha beta equals the trace. Yeah. So, well, I'm going to ask, of course, what the trace of h bar is. And the trace of h bar, which is g h bar, actually, before I do that, I'm going to say that there's other notation for this concept here. The same quantity you'll see as capital H in the literature. I've seen this in the literature as well. H bar, and there's also an H star, which I've seen. So different people use different notation. I'm going to stick to h bar because that reminds me that it's got a nice relationship with h. So let's work out what the trace of h is. It's eta alpha beta, let's say h bar alpha beta equals eta alpha beta times h alpha beta, just copying from here, and I'm changing mu nu to alpha beta, minus a half eta alpha beta h equals eta alpha beta h alpha beta minus a half eta alpha beta h, oh no, there's a factor of h there, eta alpha beta and then the h, that's right, equals h by definition, because it's that, minus a half times g alpha beta, sorry, eta alpha beta times eta alpha beta is just 4. It's probably worth going through that. That's sigma over alpha, sigma over beta of eta alpha beta, eta downstairs alpha beta. So if I write out the full metric tensor like that, for the standard metric tensor at least, we've got 1, 2, 3, all plus, and of course a minus times a minus is a plus, so that's another plus 1, so we've got 1, 2, 3, 4, times h equals h minus 2h equals minus h. So what have I done there? What I've done is shown that the h bar alpha beta times eta alpha beta, which equals the trace of h bar, equals minus the trace of h. So that's why you call it the trace reversed perturbation. So h bar alpha beta equals h alpha beta minus a half eta alpha beta h equals that is the trace reversed perturbation. Great. I'm going to stop there. Stop. Well, why have I done this? I've done this because I'm going to start thinking about how to substitute the trace reverse perturbation into these equations here, and we'll see what simplifications we can get. As I say, it's a non-obvious substitution to make, but we'll see that it results in a mild simplification of these equations. But they're very complicated, and any simplification that we can get is certainly worth trying. So I'm just going to stop there. Stop.